Hello everyone, and welcome back to this series on the foundations of mathematics. Today we're going to be taking a little bit more of an abstract direction in terms of what we're going to be discussing, and we're going to be looking at functions as objects. Similar, numbers are objects, sets are objects, and functions, technically speaking, are objects as well, because they transform one set into another set, amongst other things as well. So let's take, for example, we have f of x is equal to x squared minus 5, and we have g of x, which is defined to be 3x minus 2. And let's take, without loss of generality, that the domain of f and also the domain of g are both taken to be the set of real numbers. So if I were to say, what is 5 plus 5? You would obviously say 10. If I say, what is x plus x? You would obviously say, hopefully, 2x. But what if I were to ask you, what is f plus g equal to? Right? So this operation, f plus g of x, so this is a function, and this is the name of that function. So what are we going to define f plus g, the function, the sum of functions, as? Well, we're going to define this to be equal to f of x plus g of x. So for our particular example, what would that be? So f of x is equal to x squared minus 5 plus g of x is equal to 3x minus 2. So that technically would be the answer to what is f plus g of x. Now, some people will expect you to simplify this expression. Now, it's very important that simplification does sometimes delete some important information about the function, but in this case, all will be okay. So we clearly see that we have negative 5 plus negative 2. We know that's going to be minus 7. So we can write this in descending order as x squared plus 3x minus 7. And that would be the simplified representation of the function f plus g of x. Now I want to just make a quick comment that the notation f plus g of x technically is not the distribution of x into this expression. But technically speaking, even if you were to do that, you technically will get the same definition, right? But this is not what this notation implies. So I don't want you to get that false interpretation of it. So that's what we call the sum of functions. So how would we define the difference of functions? So we define the function f minus g of x to be equal to, and you probably can already guess, f of x minus g of x. So for our particular example, what would that be? So that's going to be equal to x squared minus 5 minus 3x minus 2. And now we get into the subtraction and your basic algebra associated with variables and expressions. So keep in mind, if we have a minus in front of a parentheses, we need to distribute that minus inside of it. So once we have that, we're going to have x squared minus 5 minus 3x plus 2. And then we can combine our like terms of minus 5 and plus 2, which is going to give us a minus 3. So we're going to have x squared minus 3x minus 3. And that would be the simplified answer of f minus g, right? So we have that this quadratic minus this linear function results in this particular quadratic function, x squared minus 3x minus 3. So that's going to give us this. And now let's define the product of two functions, which some people will write as f times g of x. And some people will also write this as juxtaposition multiplication fg of x. Most of the time people will interpret that as that, but of course, as usual, always make sure that they are notating things as they intend. So traditionally, this is going to be defined as the product of the functions f of x times g of x. And for our particular example, what will that be? So that's going to be equal to x squared minus 5, and then we're going to multiply that by the function 3x minus 2. So here we can either FOIL or just use repetitive distribution. So if we use the foiling technique, what is that going to give us? That's going to give us 3x to the power of 3, and then minus 2x squared minus 15x plus 10. And that's already in descending order, so that would be the simplified representation of the product of our functions f and g. So then there's one other common operation, which some people refer to as the quotient of functions. A couple ways of representing this. Some people will use that little symbol that you might remember from grade school, and some people will use fractional notation, f over g of x, to represent it. So this is going to be defined to be equal to the quotient of the function outputs f of x over g of x. So for our particular function, that's going to be equal to x squared minus 5 all over 3x minus 2. And depending on how you define simplified, most people will usually accept this as the simplified representation of the quotient of the functions f and g. All right, so those are the main operations of functions, but there's one thing that I want to note before we get into a little bit more detail of operations with functions, and that is f of x and also g of x are not domain values, right? They are what? They are range values. And why is that? Well, keep in mind, f will send the element x to, usually we write it as f of x, and g, the function, will send, for example, x to g of x, right? So therefore, using this notation, usually what we have here is that x belongs to the domain of f, x belongs to the domain of g, and f of x belongs to the range of f, and g of x belongs to the range of g. So f of x is not a function, it is a number. G of x, again, is not a function, it is a number. F is the function that sends x to f of x, and some people will, of course, give a different name to f of x. Some people will call this y, and some people will call g of x, say, another value of y, say, for example, y2 or something like that. Right, so those are just some very important little technical details that you definitely should know. Now let's get into a couple more important things that you definitely should know when operating with functions. So let's again take our same exact functions as examples, f of x, x squared minus 5, and g of x, 3x minus 2. And let's assume that they have slightly different domains aside from a set of real numbers. Let's define the domain of f to be 0 to infinity, and let's define the domain of g to be the half-overment interval 3 to 5, inclusive of 3 and non-inclusive of 5. So let's explore, because we already know how to find the algebraic representation of the sum of f and g, but what about the domain of those particular functions? Right? So let's see if we can see how to combine or manipulate or merge two different domains. So what is the domain of the function f plus g? And let's take this very, very slowly and see if we can analyze a couple important things. Right? So keep in mind, f plus g of x is defined to be equal to f of x plus g of x. And it's very important, or maybe I guess I should say safer, to not simplify when you try to find domain and ranges of combinations of functions, because sometimes issues sort of disappear on the algebraic end, but are intrinsically still there on the theoretical side. So f plus g of x is f of x plus g of x. So in order for this function to be evaluatable at x, f of x must be able to be evaluated, and g of x must be able to be evaluated, and the sum of those particular numbers must also be able to be executed under the set of reals that we're working in. So let's look at a couple numerical examples of that. So if I ask you, what is f plus g of minus 1 equal to, well, what would that be? So f plus g of minus 1, by definition, would be f of minus 1 plus g of minus 1. So in order for this expression to make any sense, minus 1 must be in the domain of f, and minus 1 must belong to the domain of G. But the domain of f is defined to be closed interval 0 up to infinity, and minus 1 does not belong to that particular interval. Therefore, this expression does not exist. And similarly speaking, minus 1 doesn't belong to 3, 5 either. Therefore, that expression doesn't exist either. So since both of those expressions do not exist, this object doesn't exist either. So that means what? That means minus 1 does not belong to the domain of f plus g. Similarly speaking, we can look at some other values. For example, what is f plus g of 2? Well, by definition, that should be f of 2 plus g of 2. But again, 2 belongs to the domain of f, so that's perfectly okay. But 2 is not between 3 and 5, therefore this does not exist. Therefore, you can't have a number added to something that does not exist. Therefore, since this does not exist, this does not exist either. So we can clearly see that 2 does not belong to the domain of f plus g, along with minus 1. So if we look at, again, let's choose another number, for example, f plus g of 3. By definition, that would be f of 3 plus g of 3. 3 belongs to the interval 0 to infinity. 3 belongs to the half-open interval 3 to 5. Therefore, since both of those items exist, we then have that 3 belongs to the domain of f plus g. Right? And in fact, one should be able to follow this logic and prove that 3 actually is the minimum value of this particular domain. Right? And you can do similar analysis for the difference, product, and quotient of two functions as well. So you should be able to prove to some degree that the domain of f plus g will actually be equal to the domain of f intersection with the domain of g, right? So you take these two sections, you find the intersection, and that will be equal to the domain of the sum, right? And I also invite you to find a general expression, for example, for the domain of f minus g, the domain of f times g, and if you're very adventurous, the domain of f over g. But this one is a little bit more sensitive because we're dividing, and keep in mind you can't divide by zeros, so we have that slight nuance to deal with. So actually, let's look at the quotient of functions to sort of see what's going on there. So f over g of x, remember, by our example, would be equal to x squared minus 5 all over 3x minus 2. So if we choose a particular value of x, obviously it has to be in the domain of that. It also has to be in the domain of the denominator as well. And we also have that this cannot be equal to 0. In particular, for this particular example, x cannot be equal to 2/3. Right? So if 2/3 was in the intersection of the domain in these two values, you can't evaluate that at 2. For example, if you plug 2/3 into 3x minus 2, you get 0, but you can't divide by 0 for the quotient of the functions. So using that particular logic, what would the domain of the quotient be? So we can see that the domain of the quotient of two functions f over g would be equal to the domain of f intersection with the domain of g, because both things need to be evaluatable, and we need to remove or take away the set of all values x such that g of x is equal to 0. Right? And that would be the general expression for the domain of the quotient. Right? So that's how you would analyze the domain of the sum, difference, product, and quotient. But what about the range of f plus g, the range of f minus g, the range of f times g, and the range of f over g? Using a similar analysis approach, I just want to leave this exercise for you just to play with because I think it's a very good exercise to practice with. Another operation that is extremely important when it comes to functions is known as function composition. Function composition has a couple notations. The most common one of them all is f circle g of x. So this is defined to be equal to f of g of x. So keep in mind, x is the input of g, and G is the input of f. So all of the range elements of G are the domain values of f, provided it exists. All right, so let's actually write that down because that's a very important thing. So the outputs of G are the inputs of f. Very, very important. So let's take a look at what that would look like for our example functions. So again, f of x was x squared minus 5, and g of x was 3x minus 2. So what would the compositions of f with g be? So f composed of g of x, by definition again, is f of g of x. So what is g? G is 3x minus 2. So that's f of 3x minus 2. So everywhere you see x in f of x, you're going to place 3x minus 2 in that position. So this is going to be equal to x is now turned into 3x minus 2 squared minus 5. Right? So that would be the composition of those functions. Now, of course, this is technically the answer, but you can, of course, simplify this if you wish. So first thing, expand that term correctly. So that's going to be equal to what? 9x squared minus, so that's going to be 3x times 2, both negative, add to negative 12x, and then minus 2 times minus 2 would be equal to positive 4 minus 5. We can combine those constants at the very end, and that's going to be equal to what? Oh, how did that 2 turn into a 5? I don't know. Let's turn that back into a 2. And then we have 4 minus 2, which we know is going to be equal to 2. So this simplifies into 9x squared minus 12x plus 2 as our simplified final answer for the composition of f with g. Now, how can we find the domain of the composition of functions? So let's be very careful on how we write this. So again, f composed of g of x is defined to be equal to f of g of x. So what is necessary for this to be defined? So obviously the input of f needs to be defined, so that means the range of g must exist for input value x. So we can clearly see that x must belong to the domain of g, and g of x is a number as well and must belong to the domain of f, right? So therefore, what can we say? So the domain of f composed of g is going to be equal to the set of all x such that x belongs to the domain of g. And what else must be true? Well, is the set of all x such that g of x belongs to the domain of f, right? So that would be the slightly complex but the domain of the composition of f and g. So let's do a quick numerical example just to make sure we understand this particular structure. And let's take a couple different functions now. Let's take f of x to be equal to 5x plus 1, so a linear function. And let's take g of x to be equal to 2 divided by x plus 1. So every time we have that polynomial looking thing in the bottom, we usually call this a rational function. And let's assume we take the domain of f. Let's take this to be the set of reals, and let's take the domain of g to be equal to the set of reals except for minus 1, because when we divide by negative 1 plus 1, we get 0 in the bottom. And let's assume we don't want to piecewisely define that. So what would be the domain of the composition? So let's actually do a different order. Let's look at g composed with f of x. So what would that be defined as? So g composed with f is defined as g of f of x. So now f of x is the input of g. So what is g? G is 2 over x plus 1, but x is turning into 5x plus 1. So it's 2 over 5x plus 1 plus 1. Right? So x turned into 5x plus 1. Right? So that would be the non-simplified representation, but we know we can simplify that into 2 all over 5x plus 2. So that's the simplified representation. So what is the domain of g composed of f, provided that these are are the chosen domains of f and g. Okay, so it's very important to note here that -1 can be evaluated 5 times -1 plus 2. It doesn't give us an issue of 0, right? So let's actually write a wordy statement here. So a quick note. So even though -1 does not belong to the domain of G, right? Because keep in mind, f needs to be evaluatable at x, right? And G needs to be evaluatable at the range of f, right? But -1 doesn't belong to the domain of G, and that's okay, right? As long as -1 belongs to the domain of f, then everything is perfectly okay there. It could still be that -1 is the domain of G composed with f, right? Because as long as x is in the domain of f and f is in the domain of f of x is in the domain of G, then everything is okay. And similarly, one can say if -1 does not belong to the domain of f, then it's possible that -1 belongs to the domain of f composed with G, so the reverse way around, right? So what is the range of f? So keep in mind the domain of what's our interior function f is equal to the set of all real numbers, because keep in mind f of x is equal to a line 5x plus 1, and you can choose the domain to be all real numbers if you wish. Not necessarily, but you can, right? So this is what all of the range elements look like under a mapping of f, right? So we want this to be in the domain of G, right? So this must belong to the domain of G, right? But what is the domain of G? Well, G has all real numbers, so that's going to be the set of all real numbers except for -1. So that means this object, 5x plus 1, can be anything. So 5x plus 1 can be anything except for -1, right? So what x value is the only thing that violates that? So 5x plus 1 can be anything except for -1. So if we subtract both sides by 2, we get 5x is not equal to -2, which means x cannot be equal to -2/5. And if we remember what our simplification version of G composed with f looks like, what was it? So G composed of f came out to 2 divided by 5x plus 2, and we clearly see that if we plug -2/5 into this expression, that we do indeed get 0 in the denominator, which we already know is undefined. Right? So that's actually very, very beautiful, although slightly intricate at first, but once you get the hang of it, it's actually not too bad. So let's take another example, just to make sure we're comfortable with this. Example 2. Let's actually take f of x and g of x, both to be the same rational function, 1 over x, and let's also assume that the domain of f and also the domain of G are both chosen to be the same exact thing, the set of all real numbers except for 0. So we're not going to piecewisely define 1 divided by 0 to be something else. So what exactly is this? So it's also very important, if you know the range of 1 over x, of the domain of 1 over x, then you should be able to find that the range of f and also G will also be the set of all real numbers except for 0, because if you remember the graph of 1 over x, it has this star-like pattern, right? So it has this vertical line that it approaches but never touches, sometimes called a vertical asymptote, and it also has this horizontal line that it approaches but never touches, y is equal to 0, also called a horizontal asymptote. More on that a little bit later, right? So we have these particular objects. So what exactly is the domain and range of the compositions of these functions? So let's look at that. So what is f of g of x? So again, by definition, this is f of g of x, right? So what is g of x? So g of x is equal to 1 over x. So we're just going to plug that into here. So f of 1 over x. So when we look at this, keep in mind, notice that x cannot be equal to 0. If x is equal to 0, g of x is not defined. So if g of x is not defined when x is equal to 0, that means x cannot be equal to 0 for the domain of f composed of g either, because the range of g is not defined when the domain value of x equals 0 exists. Right? So if that is the case, that means x is not equal to 0 even in the domain of this particular relation, because the associated range value for g does not exist, and hence cannot be taken as a domain value for f. So once we have that, what do we have? Again, but what is f of x? So f of x also is 1 over x, so this is going to be equal to 1 over this input 1 over x, right? So that's what we have here, and keep in mind the reciprocal of a reciprocal is just equal to that value, and we're just going to be left with x, right? But keep in mind, x cannot be equal to 0, still applies to this. And that's very, very important. So we clearly see that 0 is the only issue, right? So that means 0 does not belong to the domain of f composed with g. So we can say more formally, the domain of f composed of g is the set of all reals except for 0. But when we simplify this, f composed of g, it looks like the line, or the linear function, y equals x. But keep in mind, that's the domain. So what does the graph of this look like? So we already know what y is equal to x looks like. It looks like a line with a slope of 1, but you can't be at 0. Right? So this is the graph of f composed of g. It looks like a line, but is it a line? No, because it has a hole at x is equal to 0. Right? So it has a hole. Has a hole at x equals 0. And why does it have a hole? Because the graph looks, for the most part, like this line, but it has this piece, this 1 point piece, missing. So that's why I said it's very useful to understand the overall geometry of a composition of functions before you simplify it. Because if you say, oh, this is just the same as y is equal to x, no, because it has that small little piece missing on its domain. Now that we're a little bit more comfortable with the composition of functions, I want to do one last example that appears to give a lot of people a little bit confusion, especially when we investigate inverses of functions a little bit later. So what I want to do is I want to consider two functions, f of x and g of x. F of x being the basic parabola, y is equal to x squared, and g of x being the basic square root function, square root of x. Let's assume that we take the domain of f to be the set of all real numbers. That's the largest possible domain you could choose under the set of reals. And also let's assume that we can take the domain of g, the square root function, to be the non-negative reals. Again, the largest possible domain that you can choose under the set of reals. So let's compose these two functions in a variety of ways. So firstly, let's do some basic ones. Let's do f composed with itself. So f composed with f. So what would that look like? So what is this interior function? So by definition, keep in mind this is f of x. So what is this interior function f? Well, f is x squared. So this is going to be equal to what? So that's going to be equal to f of x squared. But what is f again? That's just going to be something squared. So that's going to be something squared. And remember, power to a power is equal to the product of those powers. So that's going to be x to the power of 4. Using the analysis that we defined before, you should be able to verify that the domain of f composed with f is also the set of reals, and the range of f composed with f is 0 to infinity. You should be able to verify that both graphically and also algebraically using the theory that we've built up to this point. So that's f composed with f, and similarly we can do g composed with g. So g composed with g. So what will this be? By definition, that's going to be g of x. So what is g of x? Well, that's just going to be equal to what? That's just going to be equal to the square root of x. And what is g? Well, that's just the square root of something. So that's going to be equal to the square root of x. So we can write this using fractional powers. We can write that as x to the 1/2 to the 1/2, and then power to the power, again, you multiply, so that's going to be equal to x to the power of 1/4. Right? And again, you can rewrite that using radicals as the 4th root of x if it makes you feel a little bit more comfortable. So using either graphical analysis or theoretical analysis, what do we have? So the domain of g composed g, one can show is going to be 0 to infinity. And the range of g composed of g will also be equal to 0 to infinity as well. Agreed? So those are the two easier ones. Now let's start mixing these two functions with each other and be very, very careful when you do it. Let's start off with f composed with g of x. So that's going to be, by definition, f of g of x. So what is g of x? Well, g of x is the square root function, so we have f of the square root function, and f is something squared, so that means this is equal to something squared. So what is that? So if you take the square root of 4, that gives you 2, and 2 squared gives you 4. So the square root of x squared is just going to give you x, provided x is in the domain of the square root function. So this is just going to be equal to x. So again, for our domain, x must belong to 0 to infinity for this piece to occur. And moreover, this is a subset of our overall range for g. Right, so that's the domain of f. So if you were to choose a value other than something between 0 and infinity, such as -2, the square root of -2 is not defined under this mapping. Therefore, the square root of -2 squared cannot be -2. So the square root of -2 squared cannot be equal to -2 under this composition. Very, very important, right? It's because I see a lot of people messing that up, right? So once you have this, as long as x is in between 0 to infinity, this identity holds. Very, very important. So what exactly is the domain of f composed with g? So from this analysis, we can clearly see the domain of f composed of g is the same as the input of g, which is going to be equal to 0 to infinity. It's going to be undefined otherwise, and the range of f composed of g also will be 0 to infinity. Now, again, you might be confused. Well, why is the range of 0 to infinity? Because keep in mind, isn't that just y is equal to x? But keep in mind, if y is equal to x is this line, but the domain of the input is 0 to infinity, then only this part of the line is going to be defined as our function. So that means this curve right here, with a closed circle at the origin, this is f composed with g, and this part doesn't exist in our graph. All right? So that's f composed with g. A couple little details there that are very, very tricky to sort of dance around, but as long as you take your time, you should be okay with them. Let's go backwards. Let's go g composed with f of x. What would this be? So by definition, that would be g of f of x. So what is f of x? Well, f of x is our x squared function, and then g is the square root of something. So this is just the square root of x squared. And remember that the square root of x squared, by definition, will be equal to the absolute value of x. So what do we got here? So x squared is defined for all real values of x. So we have no issues here. But the output of x squared is 0 to infinity. So those are going to be equal to the values that we're going to allow to be the inputs into this function, right? So because we can't have negative inputs in here, because if it's a negative input, then the square root of negative value would be undefined, right? So what would that be? So when we look at this a little bit more closely, what would be the domain? So the domain of g composed with f is going to be the set of all real numbers, because if you take any x value and you square it, you get a positive number, and that positive number can be used as an input for that square root function, right? So x squared fixes the issues for the domain of the input of the square root function, which is great. But regardless of the value you put in the square root, it will always display a non-negative number. So we can clearly see that the range of f composed of g will be equal to 0 to infinity. Right? So what would this exactly be? So if you look at this particular graph, we have this as our graph. Right? Because technically domain is all real numbers and range is 0 to infinity. So when we take the graph of this and look at it, we get this. So this is the graph of g composed with f. Right? But when we looked at the other direction, right? So close circle there, arrow there, this is f of g. Right? And we clearly see from this diagram that g composed of f is not equal to f composed with g, right? Because when we did our compositions, f of g of x, this came out to x and is not always equal to the absolute value of x, which is what f of x was equal to. Right? And again, if we look at the graphs of f and g, right? So what was f? F was this parabola, and g was this. I guess sidewards parabola, I guess you could look at it. But notice, if they were to sort of cancel each other out, because we're trying to get this y is equal to x curve, which would be this line right here, y equals x. In order for this to be, I guess, a mirror image, you would have to have, this little piece right here. But that's not there. And if g were to have it, that means g would not be a function at all, because it would have two range values associated to any positive input domain value, which is actually kind of bad. But if we take, as a slight manipulative example, if we take f of x to be equal to x squared, and g of x to be equal to the square root of x, and we're going to take domain of f and the domain of g to be equal to 0 to infinity, then what will we have? So if you actually look at the graphs of these things, so this would be f, and this would be g. Now we can clearly see that they are mirror images of each other, and you can, and I leave as an exercise for you, that if we take the domain of f and the domain of g to be both non-negative reals, then you can find that f composed of g of x and g composed with f of x, so g of f and f of g, they are both going to be equal to the same exact value. And let's stay consistent with notation here. So g f of g and g of f of x will both be equal to just the function x. Right? So that's actually very, very important. And this identity, if it exists, will be used to define another type of function a little bit later. So I hope you enjoyed this video on operations with functions, and I'll see you in the next one. Take care.